Well, good afternoon and hello, Advanced Kentucky AP Chemistry students and teachers. We are getting ready to start the fourth of our online content review sessions that will hopefully help you prepare for the AP Chemistry exam that will be given on May 14th, coming up imminently. One of the central topics will be chemical kinetics, rate laws, and mechanisms. And we are fortunate to have Alissa Clark from Bardstown High School, Alissa is also an AP Chemistry table leader, and she'll be sharing some important notes on there. Many of you know that I'm Lou Akampori, your host for today, and with my colleagues there. We'll have a few people on here in live, so just please, students and teachers, keep your microphones muted and your video turned off, but do feel free to use a chat box either to respond to questions or to ask questions. Particularly, teachers out there also be ready to help out if you're so inclined. This session and others are archived at the kyap2020.com site, along with those from other AP Math and Science and English sessions. There's also some support material from the session, so if you go back and view some of the videos, there'll be some notes and questions there. So feel free to take advantage of that or send an email to me. So once again, without wasting too much time or spending too much time before we get to our comment, here's Alissa Clark, and I will turn the stage figuratively over to her. She'll be talking about chemical kinetics, rate laws, and mechanisms. So Alissa, go ahead and share your screen.
Okay. There it is. Okay, so let me make sure I've got what I want to see here. Okay, can we see what I'm looking at?
If it's a graph of concentration of NO versus time, then yes.
Yes, excellent, excellent. So welcome students and teachers. I'm glad that you are here. It's exciting to be able to do some actual lifetime teaching, even if we're not on the same space. So kinetics is all about how fast reactions happen. So we have to measure some sort of quantity over a given period of time. And you're going to look at a lot of graphical data in these particular types of questions and this particular information. So the most important thing to do when you're looking at a graph is to look at your axes that are involved. And so we have on the y-axis the concentration of nitrogen monoxide, and on the x-axis we have time being measured in seconds. And you can notice the concentration is going down over time, so that tells us that the nitrogen monoxide is a reactant. And you can tell it's going down at a non-constant slope, so that tells us that the concentration of nitrogen monoxide affects the rate of the reaction. And as you look at a graph of concentration versus time, those should be some of the first things that you're kind of taking a look at there. Now there is a balanced equation that goes along with this that I wasn't quite able to pull over. So here's a balanced chemical equation, and one thing that you might want to be sure that you are aware of is the idea that when we measure rates of reaction, we have to measure it in terms of some chemical species that's involved in that reaction. And you need to be able to relate the rates to one another. So you can see here that we have perhaps an initial amount of the nitrogen monoxide that's maybe, let's say, 0.0028 molar. And we don't know what our initial concentration of oxygen is, but we would have to assume that our initial concentration of nitrogen dioxide is 0. And one thing that I want to make sure that you're aware of as we continue to move through this is that these graphs of concentration versus time are going to be connected to the change row of any ICE table that you might build for a chemical reaction. So for example, if we were to look at what happens in the first 100 seconds of that reaction, at the end of 100 seconds, you can see that our concentration of nitrogen monoxide has decreased to 0.0005. And so we can say, well, then we know that our change is a particular value. And then we can use our coefficient relationship to say, oh, well, because the rate of change of nitrogen monoxide and nitrogen dioxide have to be equal, they're going to change. Yes, sir?
Check your math there.
Can I not subtract?
0023, I believe.
Oh, yeah. Yeah, I can't subtract.
Yeah, I get to do something as host here.
Oh, yay. See how easy it is to make simple mistakes? My students here, I would tell you that I'm making those mistakes on purpose, but my actual students are in here and they'll tell you that's a lie. So the change in concentration of the NO and NO2 are going to be equivalent. And you could make a graph of, okay, well, how does that change over time? And I'm just kind of predicting the rest of the points there. Well, and I'm definitely not graphing that point right, am I? Because this would need to be 0.0023 at that time. There we go. So one thing I would question is, what can you tell me about the rate of change of oxygen? Can you tell me if it's going to be positive or negative? And there's no poll there, so I'll just let you think in your own head. It's also a reactant, so its rate of change will be negative in this case. And even though I don't know what the starting amount is, I do know how much it has to change by because I know the change in the concentration of the nitrogen monoxide. The amount of the concentration of the oxygen has to go down by only half as much. And so the change in oxygen will be minus 0.001. Oh my goodness. 15. Lou, you're gonna help me with my math there because I can't math this morning? Yep, okay. So, and we 0.001280. So, so keep in mind that coefficients in the equation relate to the graphical data that you will see if we express the rates of reaction in terms of one reactant versus another. Okay? Just kind of a little introduction there. So let's talk about, and I went through the list of learning objectives from the College Board's curriculum and just kind of went in order. So let's say we're tearing out a reaction between calcium carbonate and dilute hydrochloric acid, and here's a chemical reaction that takes place. That's not a net ionic equation, it's a molecular equation, so it shows everything that's involved. And so we have, let's say we have chunks of calcium carbonate, so we'd have chunks of limestone or marble reacting with the dilute hydrochloric acid, and we're going to make a calcium chloride solution, some water, and some carbon dioxide gas. So the first thing I would ask you to think about is, what are some properties that you could measure to determine the rate of the reaction? And I know the chat box is not just completely filling up with answers right there. But obviously the one thing that we're going to have to measure anytime that we're going to measure the rate of the reaction is how much elapsed time has there been, right? We're going to have to measure how much time we allowed the reaction to take place. And then we have to measure some sort of quantity that we can graph on the y-axis that's going to let us relate back to this chemical reaction. We could measure, if it's in a closed system, we could measure the pressure of that closed system. We could say, well, what's the increase from atmospheric pressure?
Since one of the products is a gas.
Since one of the products is a gas, thank you. Since one of the reactants is a solid, if we let this reaction take place in an open system, we could measure apparent decrease in mass. Since one of the reactants is an acid, maybe we could measure change in pH as the reaction is carried out. So if they give you some sort of experimental design scenario, you have to think about, how am I going to measure this quantity? Because the one thing that I can't directly measure and don't have an instrument to measure with is moles or molarity. I have to measure something else that I can then somehow translate into moles later. So What if we wanted to increase the rate of reaction? What are some methods that you could use to increase the rate of this reaction, and why do these things work on a particulate level? And this would be ones that I would hope that you might throw out there. But again, I know typing in the chat box is intimidating. So we could increase the temperature. We could increase the concentration of the hydrochloric acid solution. We could increase the surface area of the solid. If one of our reactants were a gas, we could increase the partial pressure of that gas, which would be analogous to increasing the concentration of the HCl. And so the most important thing is to think about making sure you can explain why these things are working on a particulate level. And when we talk about on a particulate level, we have to think about we have more collisions either in number or collisions that exceed the activation energy barrier. Now, both of those could happen, or maybe just one. If we increase the concentration of hydrochloric acid, a concentration of a reactant, or the partial pressure of a gas, then we're going to get more collisions in a given amount of time. And so therefore, we're going to have a greater rate of reaction. If we increase the surface area of a solid by grinding up that solid or breaking it into chunks, then a solid can only react at the interface with that solid in the whatever solution it might be in or gas it might be in. So by increasing the amount of exposed surface, we're going to increase the number of collisions that are available to happen. If we increase the temperature, we're going to increase the number of collisions. That's true. But the more important factor is we're going to increase the number of collisions that exceed the activation energy. And we're going to talk some more about that later, but I just want to point it out right now, that both of those factors do increase, but the number of collisions at anything that's at an appreciable temperature is huge. And, you know, it's kind of like if you give Bill Gates a couple dollars, it doesn't really matter. The number of dollars he already had was so big it didn't make a difference. Okay, so it's the number of collisions that exceed the activation energy. And then there's a fourth factor that can be used with some reactions that we'll talk about catalysts in a minute as well. So my big key takeaway to you is if they ask you this type of question, make sure you answer the question that they ask. So when we talk about on a particulate level, make sure you're using the words particles in your answer and what those particles are doing, right? Particles will undergo more collisions. More of the collisions between the particles will exceed the activation energy. Use the vocabulary of the question. So one thing that you might be asked to do is to determine the rate law for a reaction given a table of data where you have the initial concentrations of reactants, and then you have an initial rate of formation or consumption of some reactant or product. And so if you'd like to open up the polling, we'll let students have a minute or two here to think about what their answer might be, put their answers in, and then we'll work through this problem.
And teachers can join in also. You don't have to put in the right answer.
You know, Lou, because of the way I must be working mine, I don't see the polling on my end of the screen if you've got it open, which is okay with me. but you'll just have to tell me when you've closed it and what the answers were, okay?
Thanks, Wendy. I was muted. I'm going to end the polling in 3, 2, 1. There we go.
Okay.
Can you see that?
I can't see the polling with I guess where I'm sharing my screen, maybe the program I'm using doesn't show. So
well, we had 2 votes for B and 1 vote for A. And
okay.
a lot of agnostics there. A lot
of people who weren't quite so sure. Fair enough, fair enough. So when I attack these kinds of problems, the first thing I like to do is look at my numbers in scientific notation. And I like to look at the numbers where the exponents are the same and say, okay, so I can compare the coefficient part of these numbers. I'm going to ignore those exponents. And then I'm going to be able to say, well, if the 5 was times 10 to the negative 4th, the 1.25 being times 10 to the negative 2nd, that's 2 powers of 10 bigger. So really, I'm going to consider this number to be 125 because my students don't like exponents or fractions or decimals, and anytime we can work with whole numbers, our lives are better, at least in my experience. So that's kind of the first thing I do. From there, I would look at my data, and what I'd like to be able to find is a set of experiments or trials where I can change one variable and have the other variable remain constant. So for example, I'm going to compare experiments 1 and 2. And what I notice in experiments 1 and 2 is that the concentration of B is a constant. And so what that tells me is B cannot be affecting the rate of reaction between experiments 1 and 2. Any change in the rate of formation of C is due solely to the change in A. And so the concentration of A is doubled. So A doubles. That's raised to some exponent or reaction order. And when we double A, that has an effect on the rate of formation. Well, 5 is twice as much as 2.5 as well. And so what I can see by looking at that relationship is whatever happened to A here, also whatever factor of increase of A also resulted in the same factor of increase for the rate of reaction. And so therefore the exponent with respect to A must be 1. And that lets me eliminate answer choice D. Well, crap, that wasn't a very helpful elimination, but okay. And then you can do the same thing with the other reactant. So I'd like to find a case where the concentration of A remains constant, not because I don't know what effect A has, but just because I don't like to do more math than I have to. So if I have a case where I can ignore A, all the better. And that comes in experiments 2 and 3. A is a constant. I know it's not affecting the rate of the reaction. So 0.1 to 0.5, that's a 5 times increase. 5 raised to some power. Well, 125 is how many times bigger than 5? 25. And so 5 raised to what power would give us 25? So in this case, the exponent with respect to B has to be 2. And so that lets us choose B as our rate law. So this is one type of problem that you might need to understand for the upcoming exam. Who wants to ask a question? In the chat box. You can even choose to ask it privately and change it to Mr. A. And so nobody else knows you asked the question.
So this is a commonly called the method of initial rates, and you should, and none of they can get quite complicated, but none of the questions you're going to see in 2 weeks will involve anything that would require a calculator. So, this is a good question because it shows you that numbers are going to be pretty easy and straightforward.
Yes, I think so. All right, so with that introductory question, I want to look over here at this side. Huge part of my student struggles are knowing exactly what all these words mean and what I'm supposed to be doing with them. So please make sure that you don't mix up the terms, these 3 terms, when it comes to kinetics. When we have a rate law or rate expression, that's when we have rate equals K times a concentration to some exponent times another concentration to some exponent. Well, let's see if we can, wow, I really changed that around. Okay, it worked. Rate constant is this quantity that is merely a constant of proportionality that we multiply our concentration results by, so we get the actual numerical value of rate. A really fast reaction is going to have a big rate constant. A really slow reaction in general is going to have a very small rate constant. And K is dependent upon the reaction that is happening and the temperature at which it's happening. So the only factor for a chemical reaction that happens in a particular way, the only way we change K is by changing the temperature. Increases the temperature, increases K. Reaction order is the exponent. So when we talk about what is the order with respect to a particular reactant, then we're talking about the exponent. Sometimes you'll be asked, given some information and asked to predict, well, what factor what is the exponent? And it's just like the question we just did, they just don't show it to you in a table form, but it's exactly the same kind of idea. So if you look at question 1, suppose the concentration of reactant X is tripled and the rate of reaction increases by a factor of 9. What order is the reaction with respect to X? And we have some choices there. So if you'd like to open up a poll, Mr. A, we'll see if they like this one any better.
Okay, should be open. And we're getting some responses.
Yay!
Ms. Clark, can you see any of the responses?
I can't see the polling. I don't know what I've done with, I don't know how I don't know. I got a tablet to be able to do this remote teaching with, and I don't know that I know completely how to use it.
Well, you're way ahead of me.
So you just tell me when it's time for me to keep talking.
Okay, well, we haven't had a response in a while, and we've got a few responses, and I'm going to close the polling in 3, 2, 1, and our results are C was the overwhelming choice, but there were a few votes for B.
Okay, so when we look at setting this up, we want to say, okay, what is the factor, what happened to X? X was tripled. And when we triple that X, actually, yeah, that's this guy right here. Right, we're changing our concentration. And we want to know what exponent is causing that reaction rate to change. And that's going to be equal to our rate increases by a factor of 9. So 3 raised to what power equals 9 is how we get 2 in that case. If the reaction is going to be first order, then the exponent is 1, and any number raised to 1 is itself. So whatever factor you change the rate by, whatever factor you change the concentration by, you change the rate by the same factor. See if you can try 2. Suppose the concentration of Y is doubled and the rate of reaction is unchanged. What is the order with respect to Y?
And I've relaunched the poll, and while students are thinking about this, and I guess some of you probably already knew this was coming, but remember the order does not mean a reaction goes fast or slow, and it's not that 0 order reactions go quickly or second order reactions go slowly or vice versa. They just tell you how the reaction rate varies when you vary the concentration of that particular reactant. So I'll give you a few more seconds for those of you who care to chime in with an opinion. And I'm going to end the polling now in 3, 2, 1. And it looks like this, we've got about a 2-to-1 ratio. 6 students chose A and 3 responses were B. So Ms. Clark, why don't you explain what the right answer is and where those misconceptions come from?
Sure thing. So when we have our concentration of Y is doubled, and then changing Y is going to have some effect, because if we increase the concentration of Y, we're going to have more collisions between particles of Y and whatever else they're supposed to be reacting with. And so they could, increasing the concentration of Y can change the rate of reaction because we're increasing the number of collisions in a given period of time. The exponent tells us what factor those changes happen by. The rate of reaction is unchanged tells me that this number right here is 1. I didn't double it, I didn't triple it, it didn't go up by a factor of 9, it is unchanged, it is the same number. So I increased the concentration of Y, but I had no effect on the rate of the reaction. That must mean that the concentration of Y does not affect the rate of reaction, which essentially means Y isn't a variable in my rate law. I need Y to not be in that equation at all. So what exponent could I raise the Y variable to so that it essentially kind of has no effect? And anything raised to the 0 power is 1. So 2 raised to the 0 power is 1. And so then 1 equals 1. And so the reaction is 0 order. Because if I were to plug in 0 for the exponent, then Y to the 0 power is 1, and I wouldn't have Y as a variable in my equation at all.
And Ms. Clark, we had a question, really essentially saying, how could a reactant not affect the rate of the reaction? Or how could the concentration of a reactant, if it's got to be in the reaction, not affect the overall rate of that reaction?
That is an awesome question. I really appreciate that. So we're going to talk about how that's going to be possible in a little while when we get to mechanisms, but just a little kind of a preview for your thoughts there. Reactions happen in many cases as a series of steps. And so what this tells me, because Y is not a part of the rate law, is Y must be involved in some later part of the reaction after the slowest part has happened. And so that's kind of why Y doesn't particularly matter. You might think of it like, it doesn't matter how, if there's a traffic jam getting across the bridge, it doesn't matter how fast you can go once you get across the bridge until you get through the traffic jam. So Y is like out there after you've gotten through the jam. Everything depends on what that slowest process is, and that must involve A, because A is what is determining the rate of the reaction, I guess, in that example that I have. Did I answer your question?
I think so.
Okay. All right. Whoa, that is a big thing there. So here's another question. It's again the same kind of idea for some practice. So a reaction is first order with respect to D and second order with respect to E. Which of the following would result in no change to the overall reaction rate?
I'm going to So there's a little bit of reading to do here. And remember, there will not be any multiple choice questions on this year's exam, but this sort of thing can be asked in a short free response question. I expect the free response questions will be short so that students can enter them without a lot of words. And this is the sort of thing you should be ready for. So I'm going to end the polling in about 3, 2, 1. And it looks like D was the most popular choice, with A and B also receiving votes.
Okay, so I'm glad to see nobody chose C, because if we want the reaction rate to not change, we're going to need one of those things to go up and one of those things to go down. So doubling D and doubling E is not going to work. What I noticed when I read the equation, when I read that scenario, I wrote down my rate law. Rate equals K times D to the first power times E to the second power. So what I noticed is whatever I'm doing to E is going to have the same effect 2 times on the rate as whatever I do to D. So for them to cancel out, I'm going to need the change in D to be greater than the change in E. So I need the change in D to be greater than the change in E, because E's effect is going to be squared and D's is not. So that's why I'm going to be able to eliminate B. So let's try D. That was the most popular one. This is kind of how I would do this. If I increase D by a factor of 4, and I have E, and whatever I do to E is squared, so 1/2 squared is 1/4, and so 4 times 1/4 is 1, which would be no change in the overall reaction rate. Doubling D and having E, choice A, would work if D and E had the same exponents as each other. Okay, so let's switch our ideas here just a moment. One thing that they do mention in the curriculum is, what if you will need to know what the unit on the rate constant K is? Well, there's some algebra determination and things that can be done there. It's dependent upon the overall order of the reaction. So the overall order is the sum of your exponents in your rate law. The rate is always going to be measured in units of molarity, or if it's a gas, it could be atmosphere, some sort of pressure unit, and then a time quantity to the -1 power. That's always kind of what we're measuring our rate in. So essentially, if the sum of our exponents isn't 1, then we have to have some sort of unit on K to deal with those either extra or missing molarities and provide that inverse time. And so I've taught this lots and lots of ways, and I really much prefer working out all the algebra, but my students much prefer this little job right here. The unit on K will equal molarity raised to the 1 minus overall order time to the -1 every time. So now you can't put T in there. You have to see, well, what units of time are being measured. If it's radioactive decay, it might be millions of years, right? If it's some sort of combustion reaction, it's going to be seconds. So for this example, let's say we have rate equals K times A squared times B. So our overall order is 3. The sum of our exponents is 3. So the units on K would be molarity 1 minus 3 time to the -1. Or molarity to the -2, and then let's say it was measured in seconds to the -1. And again, that's just an algebra manipulation, really, is all that is. What this does for you, though, is it lets you know what the order of a reaction is with respect to a particular reactant. I think the one that's probably most useful to know is if the reaction is first order, then the units on K are just going to be time to the -1. because when you plug the overall order of 1 into that equation, 1 minus 1 is 0. You don't have molarities on K. So you can look at the unit on K and use that to know what the order of the reaction is, if there's a single reactant generally. Okay, so kinetics is full of graphs. And you need to kind of be able to recognize those graphs and make sure that you understand when you're using them, why you're using them, and how you're using them, what they tell you. So the graph, the shape of the graph will be dependent upon the order of the reaction. And so you can oftentimes use a graph to predict the order of, or determine what the order of a reaction is. So in the first column of graphs, we're graphing the concentration of a reactant versus time. Okay, concentration of a reactant versus time. When I look at that graph, I can look at the slope of that graph to tell me the rate of a reaction. Okay, the steeper the slope of that graph, the faster the reaction is going. So for 0 order, the rate of the reaction is a constant. And so the graph has a constant slope. For first order, it decreases at a particular rate. And for second order, it decreases at a steeper rate. This middle column is a graph of, and I don't have my y-axes labeled, we are graphing rate versus concentration. How does the concentration affect the rate? So if the reaction is 0 order, then our rate law would be rate equals K. And the graph would be a non-zero horizontal line. If we were to have a first order reaction, we would be graphing rate equals K times A. And we would have a constant straight line slope. If we were to have a second order reaction, rate equals K times A squared. As the concentration of A increases, the rate of the reaction increases at a rate of 2 of those A's every time. So be sure that you look at your y-axis and think about what they're showing you, because most of the time what we see are either the graphs in the first or third column, but every now and then they'll throw that middle one in there and people get confused, right? If they show you rate on the y-axis, then the equation that they're showing you is the rate expression or rate law. That's the graph for the rate law. The last column is essentially a mathematical manipulation of the first. And it's to linearize the graph so that we have a y equals mx plus b relationship. So in the case of a 0 order reaction, it's already a linear relationship. We don't have to do anything with that. So concentration versus time is a straight line graph, and the slope of that graph is the negative rate constant, or K. If, when we take the natural log of the concentration versus time, we get a straight line graph, that tells me that the reaction is first order with respect to that reactant, and the slope, again, is the negative rate constant. If we graph the reciprocal of the concentration versus time, and we get a straight line graph, then that tells me that the reaction is second order with respect to that reactant. And the slope is K, because the slope of that graph is already positive. You don't have to change the sign. So if they give you, or they show you, graphs where you have taken the natural log or the reciprocal of the concentration, what you're looking for is you're looking for the graph that is a straight line relationship. This relates back to integrated rate laws and some calculus that you may or may not have some background in. You don't have to know the calculus. You just have to know that natural log of concentration versus time tells me first order kinetics. Reciprocal of concentration versus time is being linear tells me second order kinetics. And if it's a straight line without manipulating anything, it's 0 order kinetics. who wants to ask a question about that?
And perhaps we should just comment that these graphs really refer only to decomposition reactions where there's only one reactant, or in more general reactions where one reactant is in very limited quantities and the other reactants are in large excess, because then it's the limiting reactant that will determine the kinetics of the reaction.
Very good point there. So sometimes they'll something like this where you have, let's say we have X and Y doing something. And so we might have, notice I've got my graph, breaking my graph up here. We might have like 10 to the 4th concentration for Y. And so its concentration, although it might decrease, would be extraordinarily tiny of a decrease and small enough to be insignificant. Whereas down here, we could measure what does the change in X actually look like. And this is a lab technique called flooding. So essentially you can flood your reaction mixture with the reactant that you don't want to study so that any change in it becomes insignificant. Thanks, Mr. A.
You're welcome.
Okay, so let's take a moment here, and I know I've kind of given my knowledge away here, but so one thing that you do want to be sure you understand is a half-life of a first order process. So one way that you can predict, so if they give you on the y-axis natural log and you have something that's not a straight line, and they give you something that's reciprocal and you do have a straight line, you can go, oh, this is the one that's linear and reciprocal corresponds to second order, and that's great. But what if they give you the amount remaining and it's not a straight line, and that's all they give you? They don't give you the linearization, and you have to pick out one. You can use that amount remaining graph to determine if it's 0 first or second order. Obviously, if that graph is linear, it's 0 order. If it's not linear, then it's either first or second order. So one interesting thing about a first order reaction, ooh, that's not at all going to get there, but okay. Let's try that instead. Is for a first order reaction, it has what we consider a constant half-life. So if it takes a certain amount of time for the amount of material present to decrease to half or 50% of its original amount, and the reaction is first order, then that time is going to be a constant value. The amount of time required to go from 100 to 50 is going to be the same as the amount of time required to go from 50 to 25. It doesn't like me making a dot. Which will be the same as the amount of time required from going from 25 to 10 and a half. I'm sorry, 12 and a half. I did math. And so on and so on. And so what you can do if they give you a graph like this is you can go, well, okay, what is my initial starting amount? Cut that in half. See how much time that takes. So, okay, let's cut that in half again. See how much time that takes. And if those two increments of time are equal, that tells me it's a first order reaction. If those two increments of time are not equal, that tells me that's a second order reaction because it doesn't have a constant slope. Essentially on AP chemistry, those are your three choices: 0 first and second order kinetics. So on here I have number of half-lives, 1, 2, 3. And again, this is related back to your reaction, your rate constant K, where the half-life of a reaction is equal to 0.693 divided by the rate constant. And that's an equation. It's on your equations page. They're telling us there's not going to be a lot of math problems on there or math that can't be relatively easily done, but that's a relationship that is available to you. That only works for first order kinetics. Only works for first order kinetics. Okay? So, all right, let's see. if we can try that question. So we have for two first order reactions of different substances A and B, or I'm sorry, A and X, A becomes B with a half-life of 30 minutes, X becomes Y with a half-life of 60 minutes. So it says this means, answer choice A, doubling the concentration of A will have half the effect on the half-life that doubling the concentration of B will have on its half-life. B, a certain number of grams of A will react twice as fast as the same number of grams of X. C, a certain number of grams of X will react twice as fast as the same number of grams of A. D, the rate constant of A to B is lower than the rate constant of X to Y. Or E, 3 moles of A will react more rapidly than 3 moles of X. And Lou, I don't know if you're muted or not again, but I don't hear you.
I was muted, but I also wasn't saying anything, so. There is a little bit of reading here, so I'm going to give our students a chance to vote.
I appreciate that.
And there is an F on the poll, which would be none of the above, but don't use that, folks. All right, I'll give you a few more seconds and then close out the polling here. And 3, 2, 1, and so we had a few E's come in at the end, which was actually my choice. A and B were the popular front runners. So Ms. Clark, why don't you explain where the right answer is and what those misconceptions might be?
Absolutely, absolutely. So the first thing I would point out with on A is remember that half-life is related to the rate constant. And rate constant is only affected by the temperature. And so if rate constant is only affected by the temperature, the half-life can only be affected by the temperature as well. And so that's kind of one way you can eliminate A. Concentrations don't have effect on half-lives because they don't have effects on the rate constants. Will it make the reaction happen at a faster or slower rate? Sure, but not the rate constant. Okay, so and so therefore not half-life. The reason why B is tempting is because if it had said moles, it would have been the right answer. A definitely reacts faster than X because it has a smaller half-life, which means it has a bigger rate constant, actually. But when reactions happen, they happen based on numbers of particles, not how massive the particles are, right? Numbers of grams of A and numbers of grams of X could be drastically different numbers of particles of A and X. And so for fair comparisons of substances, we always have to compare them in terms of moles, right? We always have to compare things in terms of moles. And that's a major misconception issue that students always have with chemistry. Right? If we could invent a molometer to measure moles directly, we'd have huge amounts of chemistry problems solved for everybody. But the reason why we measure mass and volume and quantities like that are so we can determine how many moles or amounts of particles are there. Okay, so here we are to our reaction mechanisms, the idea of how can Y be in the reaction but not affect the rate of the reaction. So when we look at the chemical equation, really it's showing us the ingredients and then the finished products. Right, so it's all the stuff that comes out of the cabinet and then it's the box of brownies at the brownie pan at the end. It doesn't show us step by step how those ingredients are combined together in a series of steps to come up with that finished product. That's told to you by a reaction mechanism. Reaction mechanism is a series of elementary steps. An elementary step is either a collision of two particles or decomposition of a single particle. by which a reaction is thought to occur. So some reactions are single steps, and the mechanism is the balanced equation because it's just a collision of two particles or just a decomposition of a single particle. But most reactions happen by a series of steps. An overall chemical equation does not give you information about the rate law and what the exponents or orders in that rate law will be. The coefficients of an elementary step do give the exponents of the rate law for that step and that step only. And the slowest of the elementary steps determines what the overall rate law for a reaction is going to be. And I think that's kind of the key thing to walking away from a mechanism idea is it's the slow step that determines what we have to consider. What's going to happen, what reaction is going to happen. So here is an energy profile for a reaction. So if I were to think about my balanced chemical equation, I would be seeing this arrow products. And that's all I would see. I start with this stuff, I end up with that stuff at the end, and oh, here's how exothermic it is, and here's how much energy I get per mole. When we look, though, at the process by which the reaction happens, you can see that this reaction happens through a three-step mechanism where the reactants become intermediate 1, intermediate 1 becomes intermediate 2, and intermediate 2 becomes the final product. And those are a series of steps that the materials will go through until we finally get to products. And so as we look at these diagrams, the reaction with the highest activation energy, which is the energy difference between the reactants of that step and the transition state, the step that has the greatest activation energy will be the slowest or rate determining step. And so what that tells me is this guy is the RDS, or the rate determining step. And so any reactant that might be involved in this third step of the mechanism isn't going to be in the rate law. Because as soon as intermediate 2 forms, it reacts with whatever and makes product, it's good to go. So this is an example of a multi-step energy diagram. Usually we see them to where it really only shows you the one step and you just see the overall activation energy. But it can be broken up into fewer, or each step of the mechanism. I'm trying to spit out. All right, so here's an example. We have a balanced equation for the reaction of nitrogen dioxide and fluorine. And it says that twice as much nitrogen dioxide is consumed as fluorine, and an equal amount of the NO2F is made as NO2 is consumed by looking at our coefficients. And we could graph that change versus time and figure out rates of the reaction. But we can't figure out what the orders of the reaction are by looking at that balanced equation. So when I go to look at my rate law, rate equals K times NO2 raised to some power times fluorine raised to some power. It's very tempting to go and get this 2 and this 1. And sometimes you'll accidentally be right, but most of the time you won't be. If they've asked the question well, you won't be. So if they were to say, here's this mechanism, what would the rate law be? You identify your slow step. You look at your reactants of your slow step, and what this tells me is the rate of the reaction is determined by the collision of an NO2 with an F2, a nitrogen dioxide and a fluorine combined. So rate equals NO2 to the first power, because the coefficient in the mechanism step is 1, times fluorine to the first power. The mechanism step is 1. And what you can see here, as a result of that first step, we make a fluorine atom. And then a reactant of the next step is that same fluorine atom. And that's called a reactive intermediate. A reactive intermediate is something that's produced in one step and then consumed in a later step. So when your first step is the slow step, writing the mechanism is relatively simple because you just look at the reactants at the beginning and write those coefficients become the exponents. It's a little bit trickier when the slow step is not the first step. Right? So here they're telling me that the slow step is the second step. So I'm going to do my same process, and I'm going to say rate equals rate constant times the concentration of F times the concentration of A. My problem with that, though, is F is a reactive intermediate. We're not, kind of by convention, we do not include the concentrations of reactive intermediates in our rate laws because they have to be generated by the reactants that we're actually going to add. So there's several ways that we can think about doing this, but the primary way you're going to think about this is this first step is going to have come to a fast equilibrium. And what we know about when a system is at equilibrium, that means that the rate of the forward reaction is equal to the rate of the reverse reaction, which means that rate constant times A times B will be equal to rate constant reverse times F. And then it kind of becomes an algebra exercise. Well, what if I solve for F? I'm sorry. What if I solve for F means what if I need to divide both sides by K? That's what that would mean. And so this just becomes like a constant that gets incorporated in with your other constants. And I can substitute in for the fluorine atom, or the F reactive intermediate, A times B. So rate equals A times B, which is going to be equivalent to F, times the A from the slow second step. And then, you know, we collect like terms. So K A squared times B.
And that's true. Alissa, let me just stop you for a second.
Please,
We got a question from a student who asked, you know, how do you know, or what determines which of the steps in a multi-step mechanism is the rate determining step? I may have sanitized that a little bit, not sanitized, but I hope that's what the intent was. And before you answer that, I'll just say that this whole idea of equilibrium will be the topic of next week's final content review session online for AP chemistry students. So I'll let you go ahead and address that.
Awesome. So the reality is experimental observation and trying to measure what reactive intermediates are present through various instrumental techniques. The answer for the AP chemistry exam is they're going to tell you which step is slow. They're going to give you this labeling over here.
And I think some of it has to do with the energy profile and what those reactant intermediates are. For example, any reaction that involves cleaving a nitrogen-nitrogen bond, and many of you might know it's a very strong triple bond, is not going to be the rate determining step, because that's going to happen, or that will be the rate determining step, because that will happen very slowly unless it's catalyzed. But anyway, that's probably a lesson for another day. I think our time is about up. So Alissa, if you have any final words, I'll let you pass along those words of wisdom.
Let me see what I got like 2 seconds here. I got to talk.
Go ahead.
All right. So here's a graph that you will see in gas laws, and here it is again. This is the Maxwell-Boltzmann distribution, right? So what we have when we look at these graphs are probability versus kinetic energy distribution. So the key thing about this graph is we do not care about the y-axis, right? I have to hammer this one home on my students. The y-axis is not of interest to us. What is of interest to us is what is the value on the x-axis of the peak. So generally what they'll ask us about when we look at these questions is something about temperature. And so what I can tell by looking at these two curves, which are distributions of kinetic energy, what's the probability that molecules will have a certain kinetic energy distribution, I can say that, oh, look, most of the molecules represented on the red curve have a smaller kinetic energy than most of the molecules distributed on the green curve. And so the green curve is a higher temperature and the red curve is a lower temperature. somewhere on this x-axis will be activation energy. The molecules that occur under the curve, or the collisions that are represented under the curve, have sufficient energy to potentially react. And so you can see that by shifting that curve down and to the right, we've added all these collisions that now have sufficient energy to potentially react. What happens when we add a catalyst is we're adding an alternative pathway with lower activation energy. So maybe we take our activation energy barrier and we bump it back to a lower energy. And now all these collisions, it's not that they have more energy, it's just that we've lowered the bar for success, right? We've made it easy for everyone to get an A, and more of those collisions are going to get A's. Yep, and that's it. Thank you all so much for your time.
And thank you very much. That was terrific, and I think very useful. Again, this will be archived on KYAP 2020, and please keep those cards and letters coming, or at least those chemistry questions. Good luck to all the students out there, and I think it represents a good opportunity for you. So feel free to contact us, and have a good afternoon. Bye-bye now.
Bye, thanks guys.